How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're sitting at your desk, or maybe on your couch with your laptop. You open a web browser, your fingers hover over the keyboard, and you type in a name. A simple name. It could be your favorite news site, a social media platform, a place you shop. Let's say, for the sake of argument, it's Wikipedia. Wikipediaorg. You press Enter, and in the blink of an eye, a flicker of the screen, there it is. The familiar puzzle piece globe, the search bar, a universe of knowledge at your command. We do this dozens, maybe hundreds of times a day. We think of it as simply going to a website, but how does this actually work? What simple rules make it possible for a name you type in a box in Massachusetts to summon a specific collection of data from a computer that could be thousands of miles away? Today, we're opening the black box of the Internet's address book, the invisible yet absolutely essential system that makes the entire modern web possible, the Domain Name System, or DNS. The magic we see every day is one of effortless translation. It's a magic that has become so ingrained in our lives that we've forgotten it's there at all. Think about the language we use. We don't say, "I'm going to connect to the server at Internet Protocol, address 103.100and.116.248. We say, "I'm going to Wikipedia." We use a name. We speak in human terms, and the vast, cold, logical machine of the Internet understands. This is a profound act of translation, happening trillions of times a day, all over the planet, in microseconds. It's the fluid, intuitive bridge between human language and machine language. This seamlessness is the system's greatest success, and also what makes it so mysterious. When you click a link, you are not telling your computer to find a place. You are telling it to find a thing, a name. That name could lead to a server in a data center in Virginia, or Iceland, or Singapore. It doesn't matter to you. The name is the destination. The system just handles it, and it's not just about web browsers. When you send an email, you type !someone@example.com . You are using a domain name. When your phone's weather app updates, it's likely calling out to a server with a name like weatheroppy.somecompany.com . When you stream a movie, your device is fetching data from a content delivery network whose servers are identified by names. This system is so reliable, so invisibly perfect, that the only time we ever notice it is when it breaks. And when it does, it's catastrophic. In October of 2021, a major social media company and its family of apps, we're talking billions of users, vanished from the Internet for about 6 hours. The servers were still running. The data centers had power. The undersea cables were intact. But from the perspective of the global Internet, they simply ceased to exist. Why? Because the DNS records that acted as the signposts pointing to their digital front doors had been withdrawn. The Phonebook entry had been erased. For 6 hours, you could dial their number, but the operator would tell you no such person had ever existed. That's how fundamental DNS is. It's not just a feature of the Internet, it is the map that makes the territory navigable. Without it, the Internet is a trillion disconnected islands with no names and no bridges. So how did we arrive at this invisible, powerful system? To understand the elegance of the answer, we first have to understand the sheer, brute force clumsiness of the problem it was designed to solve. We have to go back to a time before the web, before domain names, to the very dawn of the Internet itself. We have to go back to a single text file. In the late 1960s and 1970s, the Internet wasn't the Internet. It was the ARPANET, a small experimental network built by the U.S. Department of Defense. It connected a handful of universities and research centers, maybe a few dozen computers in total. And these computers had a simple way of finding each other. They used numerical addresses. We call them IP addresses today. A string of numbers like 10.1.2.3. This was fine for the computers. They love numbers. But for the humans trying to use the network, the researchers, the engineers, the graduate students, it was a pain, remembering that 128.9.0.32 was the computer at UCLA, and 10.2.0.57 was the one at Stanford, was tedious and prone to error. We humans are not built for remembering long, arbitrary strings of digits. We are built for names. So they came up with a simple, practical solution. They created a single shared text file. It was called "hosts," txt. It was, in the most literal sense, the Internet's phonebook. It was just a plain text file with two columns. On the left, a numerical IP address. On the right, the human-friendly name, or host name, 128.9.0.32 UCLA, simple. A woman named Elizabeth Feinler at the Stanford Research Institute was the keeper of this file. She was, for all intents and purposes, the Internet's first telephone operator. If a new computer joined the network, say, a new machine at MIT, the administrator at MIT would call Elizabeth on the phone. They'd tell her the new machine's name and its numerical address. She would manually type a new line into the master "hosts," txt file. And here's the crucial part. Every single computer on the ARPANET had to have its own copy of this file. So, several times a week, everyone on the network would have to log in to the Stanford server and download the latest version of "hosts," txt. In the early days, when the network was just a cozy club of a few dozen machines, this worked just fine. It was a perfectly reasonable human-scale solution. But the ARPANET was growing, and it was growing fast. By the early 1980s, the number of hosts was climbing into the thousands. The "hosts," txt file was becoming a monster. The updates were becoming more and more frequent. The traffic from everyone constantly downloading the new version was starting to strain the network. And a new problem emerged. Name collisions. What if two different universities both wanted to name their main computer "mail server"? Who gets to decide? Elizabeth Feinler and her small team at Stanford. They had become the unofficial naming police for the entire Internet. A computer scientist named Paul Makapatris saw the writing on the wall. This system, this single centralized text file, was a ticking time bomb. It was a single point of failure. If the Stanford server went down, nobody could get an updated list. It was slow. You had to wait for the file to be updated and then download it. And most importantly, it could not scale. The network was destined to become a global phenomenon, connecting millions and then billions of machines. A single text file, maintained by a single team, was an elegant solution for a village. For a planet, it was an impossibility. The Internet was built on a core principle of decentralization, designed to withstand a nuclear attack by having no central command. Yet here was its address book, its most fundamental navigational tool, living on a single server in California. It was a philosophical and architectural contradiction. The question was no longer just about convenience. It was about survival. How do you build an address book for a network that is designed to have no center? How do you create a system for names that is as distributed, as resilient, and as scalable as the network itself? This is where we open the box. The solution that Paul Makapatris and his colleagues devised is the DNS we still use today, and the first principle to understand is that they threw out the idea of a single phone book entirely. The common misconception about DNS is that when you type /google.com, your computer sends a query to some massive central internet server that holds all the names and numbers, looks up the answer, and sends it back. This is intuitive, but it's completely wrong. It would just be a digital version of the old /hosts txt problem. One big file, one big server, one massive single point of failure. The genius of DNS is that it is a deeply decentralized, hierarchical system. There is no single master list. There is no one computer that knows everything. Instead, think of DNS not as a phone book, but as a global network of librarians. And each librarian is a specialist. Some are generalists who know very little, but they know who to ask. Others are experts in one very specific topic. When you ask your computer to find a website, you are sending it on a quest. You are telling it to go talk to a series of these librarians in a very specific order to track down the information it needs. It's not a lookup. It's a referral. It's a chase. So let's follow that chase. You type www.wikipedia.org into your browser and hit enter. What is the very first thing that happens? Your computer, your web browser, is completely clueless. It has no idea what the IP address for www.wikipedia.org is. The first place it looks is its own memory, its own cache. We'll come back to that, because it's the secret ingredient that makes this whole thing feel fast. But for now, let's assume it's the first time you've ever visited this site. Your computer comes up empty. So it has to ask for help, and the first entity it asks is a special server called a recursive resolver. Think of the recursive resolver as your personal librarian. It's not your own computer, but it's close by. It's usually run by your internet service provider, Comcast, Verizon, your local fiber company. When you connect to their network, they automatically tell your computer the address of this helpful librarian. Its one and only job is to answer your questions. You ask it, what is the IP address for www.wikipedia.org? Now, here's the key. This resolver probably doesn't know the answer either, but its promise to you is, I don't know, but I will find out for you. That's why it's called recursive. It will perform the entire chase on your behalf. So, your friendly neighborhood resolver librarian, having received your request, starts its own quest, and its first stop is at the very top of the entire DNS hierarchy. It goes to one of the root servers. There are only 13 of them, or more accurately, 13 IP addresses for them, managed by 12 different organizations around the world. These are the master librarians of the Internet. They hold the master index, but what's in this index is surprisingly little. A root server doesn't know the address for www.wikipedia.org. It doesn't know about /google.com or nytimes.com. It only knows one thing: where to find the librarians who are in charge of the next level down. Your resolver asks the root server, hey, do you know www.wikipedia.org? The root server looks at the end of the name, the very last part, the .org, and it says, nope, I have no idea, but I know who manages all the .org domains. Here is the address for the .org librarian. Go ask them. It provides the address for what's called the top-level domain, or TLD server. It essentially points your resolver to the correct aisle in the global library. One aisle for .com, one for .org, one for .gov, one for .uk, and so on. Now your resolver has a new lead. It zips across the internet to the TLD server for .org. which is managed by a company called the Public Interest Registry. It asks this new librarian the same question. Hello, can you tell me the IP address for www.wikipedia.org? This TLD server is more specialized than the root. It knows about every single .org domain in the world. But it still doesn't know the specific answer for www.wikipedia.org. It only knows who is in charge of the domain before the dot, Wikipedia. It knows who officially owns and manages the phonebook for the entire Wikipedia.org domain. So it replies, I can't give you the number for www, but I can tell you who can. The official librarians for Wikipedia.org are located at these addresses. Go ask them. These official librarians are called the authoritative name servers. This is the final destination in the lookup chain. Your tireless resolver takes the address provided by the TLD server and makes one last trip. It connects to one of the Wikimedia Foundation's own authoritative name servers. These servers are the ultimate source of truth for everything inside the Wikipedia.org domain. Your resolver asks its question one last time. Please, what is the IP address for www.wikipedia.org? And this server, this final authoritative librarian, opens its own local phonebook, looks under the entry for www, and says, I know that. That's 103.101.116.248. Here you go. The chase is over. Your recursive resolver, the personal librarian from your ISP, now has the correct IP address. It races back to your computer and says, I found it. The number you need is 103.101.116.248. It also does something incredibly important. It writes down the answer and saves it for a little while in case you ask again soon. Finally, your computer has what it needed all along. Your web browser takes that numerical IP address, opens a direct connection to that server, and requests the contents of the web page. And a moment later, the Wikipedia homepage renders on your screen. This entire multi-step globe-spanning conversation, from your computer to a resolver, to a root server, to a TLD server, to an authoritative server, and all the way back, happens in a flash, usually in less than 50 milliseconds, faster than you can blink. This hierarchical, referral-based system is the core principle of DNS. It's brilliant because it's infinitely scalable. If you want to add a new TLD, like pizza, you just have to tell the 13 root servers where to find the pizza librarian. If a new company, say Joe's Pizzeria, registers Joe's Pizza the pizza TLD server just needs to be told where to find the authoritative name server for Joe's Pizza. No single entity needs to know everything. Each layer only needs to know how to get to the next layer down. It pushes the responsibility downward, distributing the load across millions of servers around the world. It solved the hosts txt problem by shattering the single book into a billion little note cards and creating a system of referrals to find the one you need. It's a beautiful, elegant, and resilient design. It is the hidden bureaucracy that makes the seamless web possible, a silent, orderly cascade of questions and answers. But this brings us to a paradox. I just described a process that involves your request hopping between multiple servers, potentially on different continents. That sounds slow. It sounds like it should introduce a noticeable delay every single time you click a link. So why does it feel instantaneous? Why is the internet so fast if every action requires this elaborate game of telephone to even get started? The answer to that question isn't in the structure of the chase. It's in the art of remembering. This is the unseen giant of DNS, the principle that takes an elegant but potentially slow system and makes it feel like magic. The answer is caching. Caching is a simple idea. If you have to go to a lot of trouble to find an answer, you should write it down so you don't have to do the same work the next time you need it. DNS is built on this principle at every single level. The system is designed not just to find answers, but to remember them, aggressively and intelligently. Let's go back to our chase for www.wikipedia.org. That full, multi-step lookup, from the root servers all the way down, is what we call an uncached request. It's what happens when the answer is truly unknown to everyone nearby. But this is the rare exception, not the rule. In reality, that full lookup almost never happens. Here's why. When the authoritative name server for Wikipedia gave the IP address to your resolver, it also gave it one other piece of information, a number called the time to live, or TTL. This is essentially an expiration date. It says you can hold on to this answer and reuse it for, say, the next hour after that. You should probably ask again in case it has changed. So your ISP's recursive resolver, your personal librarian, stores that answer, www.wikipedia.org equals 103.101.116.248 in its memory, its cache. Now, imagine your neighbor, who uses the same ISP, opens their browser a minute later, and also types in www.wikipedia.org. Their computer asks the same resolver for the same address, but this time the resolver doesn't need to do the chase. It doesn't have to talk to the root, the TLD, or the authoritative server. It just checks its own memory and says, "Oh, I know this one. I just looked it up. The answer is 103.101.116.248 . The response is immediate. The entire hierarchy is bypassed, since popular websites are requested by thousands of people using the same ISP. The resolver's cache is incredibly effective. It serves up the vast majority of answers instantly from its own memory. But the caching doesn't stop there. It happens even closer to home. Once your resolver gives the answer to your computer's operating system, Windows, macOS, Linux, also saves it in its own DNS cache. So if you close your browser tab for Wikipedia and then open it again 10 minutes later, your browser doesn't even need to ask the resolver. It asks your operating system, which says, "Yep, got it right here," and provides the answer instantly. And it gets even closer. Your web browser itself, Chrome, Firefox, Safari, maintains its own even smaller and faster cache. If you click a link on the Wikipedia homepage that takes you to another page on Wikipedia, the browser already knows the IP address. It doesn't even have to ask the operating system. It just knows. So the full hierarchy of caching looks like this: browser cache, operating system cache greater than ISP resolver cache. Only if all three of those come up empty does the full, recursive lookup process even begin. This is the profound aha moment of DNS. The system is architecturally designed as a slow, careful distributed chase, but it is practically experienced as an instantaneous lookup. Its speed comes not from the efficiency of the lookup process, but from the pervasive, multi-layered system of memory that ensures the lookup process is avoided whenever possible. The real work of DNS is not in finding information, but in distributing and remembering it for just long enough to be useful. It is a system of organized, temporary forgetting. The TTL value is the key. It allows the owners of a domain to balance performance against control. A long TTL, say 24 hours, means the answer will be cached widely, making the site load quickly for everyone. But it also means that if you need to change your server's IP address, it could take a full day for the old, cached answer to expire across the internet. A short TTL, like 60 seconds, gives you more control to make quick changes, but it forces resolvers to check back with your authoritative server more often, increasing its workload. This cascade of memory is the invisible engine of the web's performance. It's why clicking a link to a popular site feels like it loads from next door, even if the server is on the other side of the planet. Because, in a way, it is. The answer, the most critical piece of information needed to start the connection, was, in all likelihood, already stored just a few milliseconds away in a cache at your ISP, or even right there inside the silicon of your own machine. So we journeyed from a simple, magical act, typing a name and summoning a world, down into the depths of the machine. We traveled back to a time of a single, humble text file, _hosts, txt, managed by a single team with a telephone. We saw how the core principles of the Internet itself, decentralization and resilience, demanded a new solution. That solution was not a bigger, better central book, but the opposite, a system with no center at all. A hierarchy of specialists, a chain of referrals, a globe-spanning, orderly chase for a single piece of information. The first principle of DNS is decentralization. It distributes the burden of knowledge, so no single part of the system is a single point of failure. The second principle is hierarchy. It organizes the infinite namespace of the Internet into a logical tree, from the root down to every individual machine, allowing for efficient navigation. But as we discovered, the final and perhaps most important principle is memory. The pervasive, intelligent caching that happens at every step is what transforms this robust, distributed system into something that feels instantaneous. Understanding DNS is understanding the Internet on a deeper level. It reveals that the network is not just a collection of wires and computers, but a complex, living ecosystem of protocols and agreements. It's a system built to solve a fundamentally human problem: our need for names. Computers would be perfectly happy with a world of numbers. We built this entire intricate global infrastructure of translation for ourselves. It's a testament to the idea that the most powerful technologies are often the ones that disappear. The ones that work so well, they become the invisible foundation upon which we build everything else. The domain name system doesn't just find websites. It embodies the core philosophy of the Internet itself: a trust in distribution over centralization, a design for resilience, and an elegance that emerges not from a single brilliant plan, but from a simple set of rules applied at a global scale. It is a quiet miracle of digital bureaucracy, the silent, orderly conversation happening in the spaces between our clicks, constantly translating our human intentions into the language of the machine.
You've been listening to First Principles. Until next time, stay curious.